So now we make a few more comments along those lines. I've already pointed out the two features of clouds that we're going to discuss. The actual infrastructure, which will be the initial focus again, and then the runtime or platform, which is what will be discussed particularly tomorrow. If we look at how science is done, I've already pointed out that we need large-scale supercomputers, like that Sequoia machine I mentioned with 1.6 million cores. And Sequoia actually does not have GPUs. It has this beautiful chip built by IBM, the Blue Gene chip, which is a really beautiful system and highly optimized to get good performance and good communication. And those are aimed at supporting highly parallel simulations, so that you can, if you want to simulate, say, I mean, one of the areas, say, that Sequoia will be used on is simulating fusion energy, to see how the tokamaks will perform. And that requires you to solve the so-called particle in the cell equations for the motion of electrons, and that requires this closely coupled network. So that's what supercomputers are. Then we have so-called high throughput systems. Those are very best illustrated probably by the analysis of the Large Hadron Collider, or by the analysis of gene sequences, where typically you have lots of data. I think the Large Hadron Collider actually itself has hundreds of thousands of servers devoted to doing its analysis. But the difference is they're not tightly coupled like Sequoia and like the simulation of fusion. They're loosely coupled because the events at the Large Hadron Collider can be analyzed independently. And so that's high throughput computing is important, and I say is in the US, the Open Science Grid has a big emphasis there, and in Europe, the European Grid Initiative is a major focus. Then we have then we take these various resources and federate them together with grids and build portals to access them and workflow to join the jobs together. So I already pointed out some key differences between clouds and HPC, and it's really quite simple. Namely, if you look at synchronization cost, if you go to a grid, then the machines are sitting geographically a long way apart, and you would have many milliseconds of latency between the different machines. If you go to Sequoia, those nodes have got highly optimized software, highly optimized networks. You might have a microsecond difference in the cost of sending a message between those nodes. And clouds lie somewhere between a microsecond and many milliseconds, depending on exactly how they're configured. And they tend to have gigabit Ethernet on lower performance networks. They tend to be optimized from internet access, not inter-machine access. So that says the key sort of in understanding which machines are used for what tasks. We can just look at synchronization, where grids have the highest cost, then clouds, and then HPC systems. And so that says that what I've effectively mentioned, namely clouds can run grid workloads, and that's illustrated by they could do LHC. And but clouds are not directly suitable for running your large-scale fusion simulation, because you will not get high enough performance. However, as I said, they are all just clusters, and so these key ideas like service-oriented architectures, workflow, etc., can be used in both approaches. So if you look at the sort of trend, you see clouds are going to be important. That's why some of you why we're here. High throughput systems have been very important and will continue to be important because they do provide cost-effective computing. And we're going to still need grids, because grids, all this data I mentioned, the data deluge, that data is always distributed. I mean, commercially, a big use is support of smartphones. Those smartphones are all distributed. And so we do have grids of smartphones and things like that. And for science, we have grids of gene sequencers and grids of environmental sensors which gather the data. And then we have the supercomputers, which are critical, and they're doing large-scale simulations. And this is just showing how we're going to get to exaflop. Blue gene is, Sequoia is sitting there at 16 petaflops, and we're meant to get to an exaflop, 10 to the 18th operations per second by around 2020. Of course, clouds by that time are still presumably 100 times the performance of the supercomputer. So when that supercomputer reaches an exaflop, the total power in clouds is going to be 100 exaflops. This is summing all the clouds.